All right, this section we're going to take a look at complex numbers. So we're going to expand your number system understanding. So I think it was Carl Friedrich Gauss was looking at this problem, and he's like, well, what solutions do we have to this? If I subtract 1 on both sides, and I square root both sides, and I look in all my real numbers, let's talk about our real numbers for a minute. Here's our natural numbers, the counting numbers, 1, 2, 3, dot, dot, dot. Then we expanded to the whole numbers. I can have 0, I can have nothing. Right, there's our whole numbers. And then we expanded to, hey, I can go into debt, right? Like, what are my integers? Let's include negatives now with our whole numbers. Whoops, 0, 1, 2, dot, 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 right? Well, what about fractions? I want to be able to have fractions. Let's call those rational numbers. Anytime a is over b, where a and b are integers, that's a rational number, right? So we have like a half or negative a third or whatever, negative, in a decimal form, these either terminate like 1/2, 0.5, it stops, right? Or it repeats 1/3, 0.33333333. So in decimal form, a rational number will either repeat a pattern or it will stop, right? That's our rational numbers. And then we had the set of rational and irrational numbers make up our real numbers. So the irrational numbers would be like pi, right? That 2.14159, blah, blah, blah. In decimal form, it does not repeat any sort of pattern. But we also have things like the square root of 7, same thing, that's irrational. It doesn't repeat a pattern. If I punch that in as a decimal, it just keeps going on forever. Or negative the square root of 3, or e, also a very famous irrational number, along with e, right? Who is greater, pi or e? If you ever Google that, the great pi e debate, pretty funny. But anyways, there's no answer to this x squared plus 1 equals 0 in these real numbers that you've been working with, right? There's no answer to this. So Gauss said, you know what? I want to expand these real numbers. I want to call this the imaginary unit, I. I, the imaginary unit, the square root of negative 1, which is going to open things up. So I being the square root of negative 1. But if I is the square root of negative 1, if I square that then I squared is negative 1. Okay? And so we're opening it up to what's referred to as the complex numbers, where anything of the form a plus bi, and over here is the pure imaginary numbers, anything of the form bi, like 7i or negative 2i or 1/2 I or whatever. But all of these real numbers and pure imaginary numbers make up what's referred to as the complex number system. Complex number system. A and B, by the way, are real numbers here. So like 2 plus 3i, or negative 6 plus 7i, or whatever, negative square root of 2 minus 1/2 I. All of those are complex numbers. Well, every complex number is a real number. So if you take like, let's just take 2. Can 2 be written as a complex number? Sure, 2 plus 0i. So 2 is also a complex number. So all your real numbers are complex numbers. Now we've expanded it. Thank you, Carl Friedrich Gauss, for expanding our numbering system. Now we have the complex numbers. So we're going to include the imaginary unit. Okay. Well, anything to the 0 power is 1. But I is just I. Remember, I is the square root of negative 1, which is the square root of negative 1, right? I squared. Let me actually erase all this junk on the right here. So if we have I being the square root of negative 1 and we square it, right? So I squared is negative 1. Let's go I to the third. So if you're breaking down I to the third, what you want to do is you want to take out how many I squareds do you have, and then what's your leftover. So I squared times I would be I to the third, right? There's 3 i's there. Well, we know I squared is negative 1. And I we just leave as I. So we have negative I. Negative I. What would I to the fourth be? Well, that's I squared squared. So we have -1 being squared, which is 1. Let's keep going with this. I to the fifth. Well, that would be how many of those squares? I got to go 2 of those. I can't go 3 of those because that'd be I to the sixth. So there's 4 i's and a leftover I. So that's -1 squared times I. -1 squared is just a +1. +1 I. So I to the fifth is I. Oops, that's I to the fifth. I to the sixth. What would I to the sixth be? Let's keep going with this. I to the sixth. Well, there's 3 of those I squareds. So what's -1 cubed? -1 times -1 times -1? -1. I to the seventh would be I squared to the third. There's 6 of them with a leftover I. So -1 to the third I. So -1 I. That was what I to the seventh would be. -I. And you can probably kind of see that pattern. It keeps going that way. Let's just skip down to, let's go I to the 38th. Well, how many I squareds is that? So you should have I squared goes into 38 19 times, right? So I'm like, oh yeah, 19 times 2 is 38. So I have no leftover i's, right? And the I squared is -1. So -1 to the 19th. -1 to an odd power, right? -1 19 times would just be -1. What about 359? Well, how many I squareds is that? And hopefully you say, well, it's odd, so it doesn't go into it evenly, but I can take 179 of those. 2 times 179 is 358. Right, that's 358. But remember, I have 359 of these. So I have 1 left over. So I squared to the 179, that's 358 of them. But I have 359 of these i's, right? So I have 1, I'm going to attach 1 I on the end there. So I squared is -1. -1 to an odd power is -1. -1 I, -I. All right, let's get into the standard form of complex number. I mentioned any complex number's got to be in this form: a plus bi. A and b are real numbers. I's that imaginary component there, imaginary part. So if we have the square root of -144, so I'm going to think about this as, before we say, well, we can't do that in the real numbers. Well, we're expanding to the complex numbers, so now we can do this. So that's -1 times 144. And I know 144 is 12 times 12. So I've got the square root of -1 and the square root of 12 times 12. Well, the square root of -1 is I. And I know the square root of 144 is 12. I got 2 of a kind, right? 12. So I'm just going to write that as 12i. 12i. So square root of -144 is 12i. How about this one? Square root of -36 minus the square root of -16. So I'm going to write that as -1 times 36 minus the square root of -1 times 16. Well, the square root of -1 is I. The square root of 36, that's 6 times 6 is 6. So that's 6i. Minus the square root of -1 is I. And the square root of 16 is 4. So we have 6i minus 4i. And these are like terms. 6i minus 4i, it's just kind of like 6x minus 4x. That's just 2x. So we'll just end up with 2i. Square root of -15. Now this one's not quite as straightforward. 3 and 5 make up 15. So I've got square root of -1i. But 3 and 5, that doesn't do me any good. I'm just stuck. So I just put them back together. So we just got I, the square root of 15, or square root of 15i. Let's do that next one. Square root of -80. So we got -1 times 80. Now 80 is Is that 16 and 5? Sixteen is 4 and 4. So square root of -1, I got I. Square root of 16, I got 4. So I got 4I root 5 on that. And by the way, I do prefer the I in front of the root. So instead of square root of 15I, I prefer the I root 15 on that. Let's do this next one. We got square root of 4. Well, we know square root of 4 is just a 2 minus, and then I root 16, so 4I. So I got 2 minus 4I on that. That's a good you try it problem. Why don't you guys try that next one? Pause it. Should end up with a 2 minus 3I root 10 on that. Again, we want to write them in this A plus B I form, right? That's a complex number form. So here's this next one. I'm going to use the fact that that's a common denominator. That's 7. Put them both over 7. So I got -2 minus, and then let me break up. That's -1 times 49, which is 7 and 7. So I get -2 minus, there's I. Square root of 49 is 7. This is all over 7. Notice my 7's canceled. So we just end up with -2 minus I on this one. Not a bad problem to pause on this next one if you want to. Also got a common denominator. Uh, 108 is 3 and 36. So we've got 1/6 plus square root of -1 is I. Square root of 36 is 6. We've got a 3 left over underneath. And then notice 6 over 36, that gives us 1/6. So 1I root 3 up there. So I got 1/6 plus I root 3 all over 6. Go ahead and simplify this one. We got square root of -12, so that's -1 times 4 times 3. Square root of -4, that's -1 times 4 minus square root of 2 is just square root of 2. So I got 2I root 3 times I times 2, so 2I minus root 2. Now I'm going to go ahead and distribute that. So I have 2I root 3 times 2I root 3 times negative root 2. So I got 2 times 2 is 4. I got I times an I got I squared, and then I got a root 3. Now remember, if we ever get square root of -1, it becomes I. But if I see a multiple, I've got to simplify it, like I squared is -1, right? So this will become 4 times -1 times root 3, so -4 root 3. Now let's see what we get over here. I got 2 times -1 is a -2. I've got an I, and then I've got root 3 times root 2 is a root 6. So I got -4 root 3 minus 2I root 6. The nice thing about complex numbers is now we can have solutions. We can express solutions when we had non-real solutions before. Right? If we have ax squared plus bx plus c equaling 0, and we know x equals -b plus or minus square root of b squared minus 4ac all over 2a. Let's go ahead and see what we get here. And so our b here is that -12. -12 is square minus 4. Our a is 4. Our c is 13. Is 4. So we've got 12 plus minus, I've got 144 minus so I've got negative 64. I say square root of negative 1 is I, square root of 64 is 8. So we've got 12 over 8 plus or minus 8i over 8. Both those go into 4, so that'll be 3 halves plus or minus I. So I got 3 halves plus I. I got 3 halves minus I. Those are our solutions, non-real solutions to that original quadratic equation. Go ahead and make that next one a U-try problem if you want to pause this and try it out. Alright, go ahead and check your cell, pause the video if you need to. Thanks so much for watching. See you next time. Take notes, of course. See you next time.